Hey physics fans, my name is Varun Yarabarla. This is my video report on Lab 2, Motion of a Falling Object, which is basically all about gravity and drag-induced motion. The point of this lab was to quantify motion of an object as it was affected by only gravity and then by gravity and drag force. Then, to understand how each case works through the application of Newton's second law of motion. In order to show this, a Chick-fil-A takeout bag was dropped. The motion was analyzed using tracker and modeled through VIO. The computational model and experimental model were then compared to understand how there was a net force on the system and that the object reached terminal velocity. There are two main principles that are applicable to this lab, Newton's first and second laws of motion. Newton's first law is an object in motion will keep moving uniformly unless acted upon by another force. In this lab, the object does not move uniformly because it is acted upon by other forces, gravity and drag force. Taking it further, we have Newton's second law, which is force equals mass times acceleration. Deriving that, we have velocity final equals velocity initial plus F net divided by m times delta t. Here, the net force is not zero, and we know this because there is not constant velocity. There must be at least one agent in the surroundings that is affecting the system. One is the weight force from Earth, and another is the drag force. The object will accelerate at a rate inversely proportional to its mass. This is the video. The Chick-fil-A bag is the system, and everything else is the surroundings. Once the points are plotted on the graph turns out to be curved, which shows that there's acceleration. Then, towards the end, there's constant slope, which means there's no acceleration and that the bag moved at constant velocity. The axes for the tracker file were tilted to a degree of 1.1 to account for the slight right movement of the bag. Only the y-axis matters in this lab, and the x and z are irrelevant. I chose the positive y direction to be up and the negative to be down. Taking data from trackers such as the initial position and the final time, we take that and plug it into the skeletal code that was provided, along with the ball's mass and the gravity force. We also use the same two equations from the previous lab, which can be found on my YouTube channel here and here. This equation, once again, is Newton's second law of motion. Once this code is run, with the weight force being the only force yielding to the net force, we get this. The model's predictions were very different from what happened in the experiment. The bag, in the experiment, moved a lot less than what was predicted. The model overpredicted what happened. The discrepancy that can be seen here can be accounted for the fact that the weight force was not the only force acting on the object. There's also the drag force. Before I show the model with the drag force, I want to mention another thing. I used the kinematics equation, which can be seen here, to check the final position of the object with the weight force after it falls to make sure that the model does an accurate job predicting the object's motion. This is the fundamental kinematic equation, and the model does indeed get a value of negative 7.9, as can be seen right here. Drag force is accounted for in the code by using the turbulent force equation containing the proportionality constant b times the velocity squared, which is seen right here. B was chosen by matching the model's final position with the observed motion's final position. This equation is written like this, or like this in the code, but I chose the first way, as can be seen in my code right here. The proportionality constant is right here. Now, the net force is just the sum of both the weight and the drag force, seen right here. Now I'm going to run the model. And this is a much better prediction of the ball's motion, as can be seen right here in this graph. When accounting for drag force, the model does a better job of predicting the position of the bag. In conclusion, we can say that terminal velocity will be experienced by the object with a large quantity of drag, which is a slowly dropping object that has more surface area and less density. This is what happened in my case. To make sure my bag had terminal velocity, or was very, very close to having terminal velocity, I checked it on Excel. I calculated the slope, found the change in the slope, and then I took the average of the changes in the slope near the end, which is where I thought the object seemed to be in terminal velocity. And by taking the average, I found that the change in slope was 0.002 meters per second. If I dropped the bag from a higher point, I'm sure I could have gotten even lower numbers to a point where the change in velocity was 0, meaning that terminal velocity was reached. Now let's answer the questions. What does it mean? The second model, accounting for both the drag force and the weight force, does a much better job of displaying terminal velocity. Terminal velocity is achieved because the object has enough drag that it is equivalent to the weight force going down, so net force is 0, meaning velocity is constant. Gravity was the prevalent force in the beginning, which is why the graph was originally curved. but later it becomes linear due to the zero acceleration and constant velocity from the equivalent opposite drag force. Question 2, what if? Just dropping the object will show a graph having downward acceleration. If the object was thrown down with enough of a force, say about 10, let's plug this into the model and see what happens. If the object is thrown down with enough force, then throwing it down means it will actually have a drag force that exceeds gravity, so it will end up decelerating first, shown right here in this part of the graph. It's decelerating, but eventually F net will become 0 again, and terminal velocity will be reached if the graph keeps going.